In this video, we will learn the elastic force. What the elastic force is, let's say we have a spring here, a rubber band, something which is elastic object. If I deform it, it tries to go back to its original state. Actually, this response is called elastic force. Let's say I have an extension like X, rightward. Immediately, when you extend the spring, it will produce or generate a force leftward against that deformation to bring back the system to its original shape. And if you make a compression leftward, the response will be rightward. This force is not constant. When you increase the deformation, the force will be stronger. At the beginning steps of deformation, the force versus x will have a linear relation like this. And Hooke's law tells us that here we have a proportionality like F equals kx. So the elastic force is proportional to deformation. K here is called the spring constant or elastic constant, and so on. And here the slope of this graph will be K. If you continue deforming the system, it will not be a line anymore. It will be a curve. So when it starts curving, we call this the limit of linear relation or limit of proportionality anyway. And this region in which the f versus x is not a line anymore may not have a guarantee for the system to go back to its original state. Actually, when you make a very large extension over the spring, sometimes the spring will go for a permanent deformation and it won't go back to its original size. Let's answer this question. An object of mass 1.5 kilogram is suspended by a spring attached to the ceiling. The spring extends by 3 centimeters from the unstretched length. So we hang an object like this and it's extended by 3 centimeters. The mass of the spring is negligible, so all the extension is because of this mass. Calculate the elastic constant of the spring. G, the gravitational acceleration, is given to be 9.8 meter per second squared. Okay, we suppose that the object is at rest here. At rest means that it's in balance. According to the vertical forces acting on that, mg downward and the elastic force upward, they must be equal and opposite. So F is equal to mg. Actually, F is kx, you know. K is the spring constant we are looking for, and x is the extension here. So I solve this equation for K, mg divided by x. Here, mass is given to be 1.5. We have no problem with that. And the g is given to be 9.8. But downstairs is x. X is 3 centimeters. It must be in SI units. So let's say it is 3 times 10 to negative 2 meters, or 0.03. So I put the downstairs in SI units. Finally, I will have the K to be 490 Newton per meter. Why the unit of SI unit of K must be Newton per meter? Because you know that K is F divided by X. F is Newton and X meter. So Newton per meter. Let's go to the next question. A student investigates how the spring force F varies with extension delta L of a spring. So here we have a force versus extension, an experimental graph with some data points. The graph shows the experimental results and line of best fit. This red line is let me show you this one. This red line is the line of best fit. Estimate the elastic constant of a spring. Okay, we know that K actually is the slope of this graph. So we must establish a triangle here and divide the height by the base and find the slope. Okay, how to find it? Actually, the vertical height here seems to be almost 5.8, and here the delta x seems to be 0.1 meter because it's centimeters, so I will use SI units. So I will have K to be F divided by delta L, 5.8 over 0.1, so it's 58 Newton per meter. What happens if I combine the springs? Let's say in series. I have a couple of springs set in series, and then I apply a force for extension of the system. Let's suppose that this one has a spring constant of k1 and the other k2. If the extension of the whole system is x, I'm looking for this equivalent spring constant. What do I mean by that? Let's say I put this system in a box and the stiffness of this system um, is something like K. The spring constant is K. So if I have a spring, a single spring here with that stiffness, with that spring constant K, and if I apply that force, I will have the same extension. I'm looking for this K, the equivalent spring constant. How to find it? First of all, keep in mind that as the spring constants of these two springs are not supposed to be necessarily the same. So if I apply a force like F, the extension of the first and the second might be different. So in general, I will have x1 and x2 for these two. Let's say, of course, this is the k1 and k2, the spring constant. So I can have x equals x1 plus x2. More than that, there is nothing to consume this force, to steal part of that. So this F is transferred to the first and the second likewise. So F is the same. So the second spring with the spring constant of K2 is acted by a force F, exactly like this, and same for the other. So F will be the same for both. On the other hand, I believe that if I have an equivalent spring here with this spring constant of K, and I apply a force of F here with the extension of X, F is equal to Kx. So K might be something like F divided by X, okay? Or X is going to be F divided by K. So here I can use F divided by K, and for X1, F divided by K1, and for X2, F divided by K2. Why the F is the same? As I told you, there is nothing to steal the force. The force is immediately transferred to both springs. So this is the relation we can immediately infer from the X equals X1 plus X2. Upstairs we will have the same F. So if I factorize from the F on the right side, I can drop them, and I will have 1 over K is equal to 1 over K1 plus 1 over K2. Mathematically, you can show that this spring constant K is smaller than K1 and it's smaller than K2. So if I apply a force like F here, and the spring constant of the second is 100 in SI units, and K1 maybe 200, this K will be less than 100 and will be less than 200, less than both. Mathematically, it's very easy to show that. Or if you want, you can rearrange this equation or write K is equal to K1, K2 plus divided by K1 plus K2 if you want. What if I put them in parallel? Parallel means they are in a combination like this. If you apply a force like F, the extension of both will be the same. Necessarily, this form of the engineering of this structure implies they have the same extension. So X is the same for both. But if this is K1 and if this is K2, as they have the same extension but different stiffness, I do not expect the same force. So here I will have a reaction of F1 from the first and F2 from the second spring. How to find this the equivalent spring constant? Equivalent spring constant means that, again, I will suppose that I have put the system in a box, and in this box the stiffness seems to be K. So if I apply a force like F, the extension like X will be the same. Okay, how to find it? It's very easy. First of all, you believe that these two forces will be the general response of the system to your extension force. So when I extend the system and keep it at rest, they are in balance. So F must be equal to F1 plus F2. Now I continue for substituting F1 and F2. As in this black box, I have an equivalent spring constant of K. So if I apply a force and the extension is to be X, F would be Kx. But F1, K1x, F2, K2x. Why the same x for the three of them? Because they are in parallel. So if I extend them, they will have the same extension. Now I can get rid of this x from both sides, and k would be k1 plus k2. Here you see that the stiffness of the combination will be larger than each. So if this is 100 and if this is 200, the equivalent spring constant will be larger than 100 and larger than 200. Actually, it's 300. There is something to be notified here. If you make this combination, it is again a combination in parallel. Why? As you see, the spring K1 and the spring K2 will have the same change in length, deformation. Although the K1 experiences an extension and K2 a compression, but anyway, they are the same. So it's not that important that if the X is necessarily extension or compression, the response is the same. So basically, we believe that this system also is a combination in parallel. An interesting question. What happens if we cut a spring into two halves of equal length? I have a spring here with a spring constant of K, and I cut it into two equal halves, okay? Then I put them here. Let's say it's K prime and K prime. Although I don't know how the K prime could be found here, but I know that it's the same as the other because they are exactly similar pieces. K prime and K prime. How to find the K prime? Okay, let's go through the reverse engineering. I know that I have already cut the string into two halves. So if I combine them again in series, I will have the same equivalent spring constant necessarily. This is a logical expectation. So if I combine these two pieces, I will have a spring constant of K. Now I apply the formula for the combination in series. In combination in series, we have 1 over the equivalent K is equal to 1 over K1 plus 1 over K2. Now K1 and K2 are both K prime. So let's have 1 over K prime plus 1 over K prime. Then I will have a common denominator of K prime and here 2. So if I reverse it, I will have K prime to be 2K. It's interesting. Each piece will have a spring constant of twice larger than the original spring. So if I combine them like this in parallel, I will have 2K and 2K. So in general, the spring constant of this system in parallel will be 4K. It's very interesting. Okay, let's continue for an example. When a load is applied to a spring of negligible mass, the spring extends by a distance L. So let's say the extension for this load on this spring is L. The spring is now cut into two halves of equal length, and the halves of the spring are arranged in parallel. So I put them like this. You know the reason of 2K and 2K here, because we already considered that. What is the extension of the parallel system under unchanged load? So I will apply the same load to this system, but what's the extension? Okay, it's not that complicated for you. I know that. Anyway, let's say the extension is x, okay? I am gonna find the x in terms of L. How to find it? First of all, I know that here, let's say the load is mg. mg is equal to kl, okay? Kx or kl here. So L is going to be the ratio of mg over k. Likewise here, x is going to be mg, the same load, divided by the total spring constant, I mean 4k. Okay, it's the same thing. You can easily see that. Let me change the color of my pen. Okay, mg over k here is exactly the L. So x is going to be L divided by 4. So extension under the same load will be a quarter of the previous extension. Okay, let's continue for another example. A spring 1 has the elastic constant K and a spring 2 has the elastic constant 2K. Okay, one spring is K and one spring is 2K. The springs are connected in series and extended by a combined distance L. So I apply a force of F and the system is extended for L. What's the effective spring constant of the serial system? First, I'm gonna find the equivalent spring constant or effective spring constant. You know how to do it. Actually, it is a combination in series, so I will have 1 over the equivalent spring constant is equal to 1 over k plus 1 over 2k. Then I make a common denominator here, 2k. It's going to be 2 plus 1, so it's 3 over 2k. Then I change it to find ke equivalent spring constant to be 2k divided by 3. It's done. Okay, this is the equivalent or effective spring constant. Part B of the question asks what is the extension of a spring 1 in terms of L. So let's say the extension is L for the system, and what's the extension of the first spring, this spring? Necessarily, as the stiffness of these two springs are not equal, they are not gonna have the same extension. I'm sure that you agree. So let's say the extension of this spring is x1 and extension of this spring is x2. Okay, this is larger spring constant. It's stiffer. So I believe that it will have less extension. The force is the same for both. You know that. So here, if a force of F is applied on this spring, it will have an extension like x1, but this one is not that easy to extend. So x2 must be smaller than x1. Actually, you can rely on your senses and say, okay, x2 is x1 over 2. Why? Because 2k is twice larger than k, so twice stiffer, maybe half of the extension. But let's prove it mathematically. I don't like to continue like this. Okay, here I have x1 and here I have x2. In general, x is equal to F divided by k. You know this F is transferred to first and the second spring, F over k. And x2 is F over 2k, okay? You know that L is equal to x1 plus x2, isn't it? On the other hand, you see that F divided by k is exactly x1, so it's x1 over 2. So here I believe that x1 plus x2 is equal to L, so x1 plus x1 divided by 2 is L, and then here 3x1 divided by 2 is L. So seems that x1 is 2L divided by 3. This is how we can find the extension of the first spring. Again, x1 plus half of it will be L. So x1 will be 2L divided by 3. And this is the answer of this part. Anyway, thank you very much for watching this video, for being with me. Take care. See you in the next video.